Hey, so welcome back. So this is the fourth video for the review, and if you can see that here, there are some conceptual questions, critical questions, and let's see what do we mean by that, and and you will get the idea that when I say the critical thinking part, that I'm trying to trigger for you here in this case. So let's have a look and see what do we mean by that. So why it is necessary to perform signal conditioning before interacting a sensor with an analog to digital converter. So you need to think about it. Why do you need to have signal conditioning before interfacing a sensor with analog to digital converter? Why we can't have a sensor directly? Now maybe a sensor has a very low signal. It needs to be amplified. Maybe the sensor, it has an output of resistance. I need to change that into a voltage or to a current. So which means the output of the sensor is not always usable, ready for an ADC. So that means the output sensor, if it is ready, that's good. But if it's not, I need to signal condition it. I need to condition it to be ready to go through an ADC. Okay, so this is the kind of an explanation of where I can reflect and see that you're understanding. Discuss how loading effects can impact the accuracy of signal conditioning circuit. Now we know the loading effects, which means that there's an internal resistance which takes part of the voltage like any divider circuit, and that's why it will affect the accuracy of my signal. So instead of having a 1 volt, I may have a 0.67 volts because it's divided between the resistance that we are having and the loading resistance. And our design strategies to mitigate loading errors is to consider a very low load in this case, or the resistors that I'm going to measure is going to have a higher value in comparison to that load effect. So these are all design strategies so that I can mitigate loading errors. Now going to circuit design, for example, a critical question will be: a sensor outputs a voltage ranging from 0.1 to 0.5 volts, but the input of a controller requires 0 to 10 volts. Now, what is the output of the voltage? 0.1 to 0.5. Now, this is like let me say like a weak signal, and I want it to be bigger. Why? Because the input of a controller requires 0 to 10 volts. So I need a larger value. So I'm going to do some kind of a conversion of this to that, 0 to 10. And again, I can use just a linear equation just to do this kind of a conversion. And so this is the step by step. Now, as I said, because this is 0.1 and this is 0, so I need to subtract 0.1, which will have this to be 0 to 2.4. And then I can find the linear relationship in this case from 0 to 0.4 to 0 to 10 volts, which will identify how much amplification I need in this case. Okay, so this is the easiest way of doing it. Yeah, it's like having an intercept of 0.1, and then you're finding the value of the amplification. Now this is simple because I said 0 to 0.4, so 0 has 0 and 0.4. I need to multiply 0.4 with 10 with I need to divide it by 4, multiply it by 100. Okay, and in this case, if I do this, so in this case, if I do this, I'm going to get 10 volts, which is like the transfer function I'm identifying to take it to this part. Design a low pass filter with a cutoff frequency of 2 kilohertz. So in this case, there is a low pass cutoff frequency of 2 kilohertz using standard resistor and capacitor values. So I'm going to assume those values. But how I'm going to assume them? I'm going to assume one of them. I have a cutoff frequency of 2 kilohertz, and this is equal to 1 divided by 2 pi RC. And now if I identify capacitor as 0.01 microfarad, I can identify what's the value of the resistor. Okay, so this is the way of how I can design a low pass filter, and then I can draw that draw that design. Now, just in case that you want to find the answer and say that, well, I want to, because you can always go back and I say I want to discuss and I want to find answer of this question. So help me with the answer. So I'm just putting in ChatGPT just for you to tell you that you can always work on it. And here it will identify for you, for example, that this is the input and this is the output. And this is what I said, that you have an intercept in this case. But you may want to get rid of the offset, which is 0.1 in this case. If you don't remove the offset, you're going to have an equation, and this is the equation that you have. The scaling factor that you have is the slope, 10 minus 0 over 0.5 minus 1, where we have a 25, so this is the slope. In this case, he calculated this, the intercept, which is minus 2.5. So this is one way of doing it, which is the easiest way. The other way is just you're saying that I will subtract minus 0.1, and then you find just the scaling factor in this case. Okay, now designing the circuit, if I want to put this equation, the ratio, I have the ratio of R2 divided by R1 is 25. Okay, so I can use this, or I may want to use a non-inverting. And in this case, you can see that he used a non-inverting amplifier, which is 1 plus R2 over R1 in this case, rather than an inverting one. So you can see that you always can have many different ideas of how to represent the solution in this case. I hope that was somehow clear to how we are trying to design a circuit. Okay, critical analysis again. Explain how a transfer function of a differential amplifier can help in rejecting noise. Now the amplifier usually it works on of doing some kind of an equation or an amplification. But how does that it help in removing a noise? Now, removing a noise, you need a filter, and this is the way that we said that we can remove noises. But in this case, because of the internal impedance that it has, the amplifier, and you can see the input impedance is essentially the input impedance of the op-amp itself, which can be greater than 100 mega ohms. And because of that helps in getting rid of the noise. Okay, so I hope that makes it clear of how this is somehow removing the noise that we have within the system. Okay, so I hope that is somehow clear for how it is removing the noise. So let's go back. Not here. Okay. Sensors and transducers. Again, I can ask about sensors and transducers. For example, a factory needs to measure both the temperature and the pressure inside a reactor. What types of sensors would you recommend? Now, I usually ask you to explain, for example, explain the piezoelectric sensor for the level. Now here I'm telling you what type of sensor would you recommend. In this case, you need some kind of critical thinking and say that, well, I need a temperature sensor and a pressure sensor. Which type of sensor I can use and how I can justify my choices. Now here in this question, that this is a very generic question. It does not identify a certain application. But if I identify the application, here it says inside a reactor. Okay. Because it said that it is inside a reactor, it may be high temperature, and it maybe need, because it's a reactor, it needs to have the temperature very accurate. So I will use an RTD in this case. and I want a linear relationship, so will not use a thermistor. I will use also an RTD. And this is why this is that, look, you can see that I'm justifying my choices in this case. And for the pressure sensor, I think so there are many kind of sensors that you can use, but maybe they suffer from hysteresis, and this could be a problem. So we have the piezoelectric sensor, that's a good one, but we have a reaction. So this reaction, I don't want it to be in contact with what I have. Maybe the strain gauge, somehow it is possible. The diaphragm, something easy, yes, because you're going to have a pressure that comes out of that reactor and pushes it on a meter here. So these are all ideas. Boarding tube is a possible answer, but it will have hysteresis. Now capacitive, it will be we don't know what kind of reaction is it, if it's going to be affected by the charges, because having charges with a reaction could be a problem, so we need to be careful. Again, if you go back, if you want to do some kind of asking and finding what are the solutions that we can have in this case, so here for example it is suggesting based on what, based on things that we don't know, we don't have enough information, and that's why I said that does it have a high temperature or not, and if it has a wide temperature range, it needs a very wide temperature range, then thermocouples could do for it. But we also can use RTD, which is more accurate and stable over time, but we're going to have limitations with the range up to 600 degrees centigrade. And now you can see that how we are trying to compare and find a suitable temperature sensor. For pressure measurement, we have the piezoelectric, as I said, but we can use all the others, you can see, and it's very difficult to decide. If you're operating in extreme temperature, then we should have a sensor that includes cooling or isolation techniques. For reactive chemicals, now reactive chemicals could be a problem. Why? Because we should ensure that the sensor diaphragm material is compatible. The diaphragm should not be reacting with the chemicals in any way. Okay, so again, I'm putting this question, doesn't mean that now you need to I'm just giving you an example of, I'll try to be more specific, give you more details if I'm going to give you some kind of this critical thinking of a problem. Okay, so here we have sensor performance. Maybe we didn't take any question about the sensor performance of GF. I will go back to the looking at the change of the pressure sensor, in which we have a strain gauge pressure sensor, and if you can look at the equation is equal to R into GF into L divided by delta L, where delta R is the change in resistance, R is the initial resistance, the GF is the gauge factor, delta L the change in length, and L is the initial length. Now looking at that, I have the gauge factor, I have the initial resistance R, and I have a 0.1% change in the length. So I have delta L divided by L. It said percentage, so that already I have a delta L over L. And we want to calculate delta R. Now everything is there. So just GF times the initial resistance times 0.1%, you're going to find the answer. Okay, so these are the questions that we have. Not going through the details, the answers are here. Okay, so I have the answers that is coming just below, so that you can look at the answers and how the first question, in which we wanted to have a signal conditioning of 0.1 to 0.5 to 0 to 10, and here it added a bias just to remove this 0.1 away, and then it added a scaling factor or a gain as follow. And I said that there is another way. This is the simplest way, but the other way is also to take the straight line equation. Low pass filter is very easy. We want a low pass filter. It didn't give me the values of R and C, but we always say, we can say that if C is equal to 0.01 microfarad, and then I can calculate what is R. Now, if we want to do the other way around, I'm going to identify R, select something that is in kilo ohms to be reasonable, and then you're going to find out what is the value of C. Okay, for the answer for the reactor, which is more suitable, we said thermocouple for very high temperature, but we don't have enough information. And we can have the strain gauge pressure sensor, where the resistance changes based on the strain that I have because of the pressure. This is the answer of the delta R, in which you just multiply all of them, 2 to 21, 2.1%. You're going to have that change of delta R. For 7, I didn't go through the details, but you can go through the other critical questions that you need. I added some other real-world applications, and again, this is just extending the knowledge and having more understanding of what you have studied. So if someone would ask, why should I have where can I have a filter? And here we are saying you can have a low pass filter in a biomedical equipment. For example, low pass filter are used in the ECG for the heart, where there is a kind of a frequency of your and the frequency comes from your heart, where it is beating a dick 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 dick. So that's a frequency, right? And if you have, and you need to make sure that you're removing any high frequency noise caused by the electrical interference. So definitely you need what? You need a low pass filter to pass the beating of the heart, that frequency, and not to be affected by the high frequency of the electrical interference. Okay, now again you will say that, well, what is the electrical interference? We have current, we have voltage and current, and definitely that would affect my system. And then I can put this in an example, in a problem. And I will tell you that you have a biomedical equipment where you need to design a low pass filter with a cutoff frequency of 2 kilohertz to remove the noise of the sensors in the industrial systems. So I can put it in a kind of a problem for you. And then I will say that I have a 50 kilohertz a power line noise. And I want you to let me read it. Filtering 50 kilohertz power line noise in an industrial environment mimics the challenge faced in an MRI. So this magnetic resonance machine that I have, where electromagnetic interference from power lines must be minimized. So I can put it in another problem, and I wanted to calculate V out over Vn and what is the attenuation that we have by having a low pass filter or a high pass filter. Okay, now where we can use Wheatstone bridge, we already took many examples, but for example, Wheatstone bridge are used in load cells for structural health monitoring of bridges. So it can be used in hospitals, for example. And I showed you just an example that's Wheatstone bridge used for with the RTD as a fourth resistor. Okay, and he just puts a load cell here in a weighing cell in a supermarket. These scales are used in supermarkets and logistics industry to measure weight with high precisions. Okay, so you can see that the change in the weight, which is the change in the pressure, if I would put it in this way, or a change in the strain. So if I have a strain gauge sensor which changes the resistance, where I can calculate delta R, as I calculated here delta R. So here I'm calculating delta R. So this delta R that I'm calculating is the change in resistance. And change in resistance, that means in the Wheatstone bridge, I can see what is the new resistance that I'm going to have based on the change in pressure or the change in weight. And this is a very accurate way of calculating in this case. I'm just giving you the example so that you can have more and more idea about how to apply these systems. And you can read more in those examples. There are many examples, and I'm just giving real world applications for those examples for your case. Please have a look and enjoy for these real world applications. And again, I'm not asking you to memorize anything of these real world applications, but this is just extending the knowledge. So I can give a problem without mentioning any real world application, but I can put it in the context of a real world application where it becomes better. Let's take an example. An ECG machine receives a heart signal at 1 hertz, superimposed with this noise, 50 hertz noise from the power lines. Design a low pass filter. So now you're going to design that low pass filter to allow 10 hertz to pass while attenuating the 50 hertz noise. Choose suitable resistor and capacitor values and calculate the frequency. So if I ask you to design this, now I did not identify what is the V out over V in, but if I said that I want V out over V in to be 98%, so the attenuation is 0.02. And in this case, based on that 0.02, I'm going to design and identify what will be the critical frequency of 0.02. If I find out the critical frequency, I'm going to assume C is equal to 0.01 microfarad, and then I'm going to find the resistance. And then here I have my pass filter. And if I go back to look at the filters, so in this case, for example, I think so here. So this is the RC filter. Okay, so I'm just showing you the filters that we have. Sorry, I should fix on this. So this is the low pass filter. So I already found what is the value of C, which is 0.01 microfarad. And based on that, I'm going to calculate the resistance based on the cutoff frequency that I have. So I'm designing this, and this design will help me eventually. This design will help me to pass the heart signal, which is 1 hertz, and it will not allow the 50 hertz. Of course, you're going to you're going to substitute 50 hertz to calculate the 50 the cutoff frequency, and then we are going to see if I have 1 hertz or 10 hertz. If I have, how much I'm going to gain. Sorry, how much going to save of this 10 hertz. So I'm going to do my calculations again and see how much I can save. So this is just an example of how we can do it. Okay, and again, if you can recall the example, and just to understand what I said. So in this case, for the low pass filter, I'm going to substitute the F, which is the high frequency. I'm going to calculate FC. Now, based on the FC, I'm going to calculate the R and C. Find R and C. And after I find R and C, it's very clear that if I have the high frequency, this is the cutoff frequency I found. So if I have a high frequency, I'm going to have times 100, 0.0099, which is 0.01 percent. So imagine, it will be 1%. So I'm having 1% will pass of the 1 megahertz. Now, how much will pass if I have 1 kilohertz, which is the low frequency? All of it will pass, which is 99.6% will pass. So you can see that I'm substituting 2 times, one for the high frequency and one for the low frequency, to know how much I'm getting rid of the high frequency and how much I'm having passing. So I'm having here only 0.009 passing, and here I'm having 0.996 passing of that 1 kilohertz. Here I'm having 0.009 is passing of that 1 megahertz. Okay, so I hope that clears up the problem that I was just trying to explain. Try to solve the Wheatstone bridge. We already went through this. This is the RTD, in which I have the equation RT is equal to RT. RT is equal to R naught into 1 plus alpha delta T. In this question, so I'm going to use that equation, but what information do I have? I have R naught and T naught. and a temperature coefficient, I have alpha, is used to monitor the exhaust temperature of a gas turbine. If the resistance measured to be 215 ohms, now I'm given R, and it wants me to calculate the T. Okay, so you need to rearrange that problem so that you can find, and this is the rearrangement. I'm just showing you the rearrangement to find the value of T. Okay, if you have, for example, a thermistor and a battery management system in which a thermistor has a resistance of 10 kilo ohms, R naught and T naught, and the value of B is 3500, and we want to calculate the thermistor resistance when the battery temperature rises to T. So if you look at this equation here, so I have R naught, I have B, I have T1 and T2. I want to calculate what is the RT, the new resistance. So that is simple, but remember that temperature should be in Kelvin. The temperature should be in Kelvin. A piezoelectric sensor, again, same story as we have solved before. So I have the piezoelectric sensor, which I think we already solved before, so I don't need to solve it again. Maybe I need to show you that just to read. So V is equal to D into sigma. And sigma is the pressure or force over area to calculate what is the output voltage. And in this case, what do I have? I have here D, which is 100. I have the force. I need the area. So that I can have force divided by area to calculate the stress in this case. So here, force divided, this is not C, and C is very confusing actually. Force divided by area. Okay, so this is the pressure, which is the stress, times D. D is 100, and the force is 500 newtons. And in this case, I understand that it's added that capacitance of C in this case, but I don't want to go through confusing you, because I explained that to you in terms of sigma in this case. Again, what I'm trying to say is that this pressure could be represented as charges or capacitance in this case, and this is why I'm having a different calculation here, but I'm going to give you the value of the area instead, so that you can substitute area here. Okay, so that's a capacitor level sensor. Again, I have ER, E naught, I have A and D, so that I can find the solution. This is ultrasonic level sensor. We didn't solve this, so this is good to solve. The speed of the sound is 1482, which is C in this case. And if the sensor measures a time delay of 0.002, calculate the distance of the water surface. Now, going to ultrasonic level sensor, this is the ultrasonic level sensor. If you can remember, the equation is 0.5 C, which is the speed of sound, into T. So going back, 0.5 here is divided by 2, which is 0.5, into C into T. Now, do we have the value of C? Yes, the answer, we have the value of C. Do we have the value of T? Yes, we have the value of T. And that's all. So if we have value of T and C, we just substitute to find what is D. And again, what is D? And D is the distance to the target. Okay, so which is the level in this case, which is the level. And last time I told you, it's measured the distance of going and coming back, and that's why we want multiplying by 0.5 to identify the distance of going only. Okay, so that is what we have here. Here, a thermocouple, an automated. We have for example, a weather station, which is automated, and it is using what? An automated weather station is using a thermocouple to measure temperature, and an ultrasonic sensor for wind speed. The thermocouple generates 20 microvolts per degree centigrade, and this is volts per degree centigrade. So we are talking here about the Seebeck effect coefficient. And the ultrasonic sensor uses C is equal to 343, which is the sound speed. Calculate the thermocouple voltage at 50 degrees centigrade. Now we know thermocouple V is equal to S into delta T. So this is the what we have here, and for the wind speed, V is equal to d divided by delta T, which is the simple equation of distance, velocity, and time. Now let's go back. So what is the question? Calculate the thermocouple at 50 degrees centigrade. So initially, what was the temperature? I'm not sure that's mentioned here. So if the temperature was 25, for example, and I want to measure the temperature at 50. So 50 minus 25, it will be 25, which is delta T. The S, I'm going to have 20, so I'm going to multiply S times delta T to calculate V. Okay, so this is simple. And then if I want to calculate what is the wind speed, I don't think so this is part of what I explained to you in the class. But if I have the upstream of 0.003 seconds and the downstream of 0.002 seconds, if I add them, I will have what is the delta T. And in this case, if I have this speed of sound, which is V, because it's the ultra sensor, yes, okay, that's good. Because we are using two sensors. We calculated them with the thermocouple and the other sensor which measures the window speed. In this case, if I have time and I have time and I have the ultrasonic sensor, in this case, this is not straightforward because the speed of ultrasonic sensor will identify the distance for me, but it will not help me with the wind speed. Now wind speed, I need the distance. Okay, good. I need the distance. I need the time. I already have the time, but I don't think so we have enough information, to be honest, so I'm not going to continue with that. Okay, so going to the problems, these are the solutions of the problems of design. And this is the Wheatstone bridge I discussed. This is the RTD and the turbine, just rearranging the equation. This is the thermistor and the battery management system using the exponential term. And this is the problem to solve for the piezoelectric sensor. It's just a problem. You divide by area. This is what we said. But if you don't have the area, you divide by the capacitance in some other arrangements. Here we have the values of ER, E naught, area, and the D. We just substitute them to find the value of the capacitance for the level sensor. For the ultrasonic, we said we just multiplied them, and it's already multiplied by 0.5 or divide by 2 to find the distance, which is the level. And the noise reduction, I didn't take that, but it's just a substitution. And this is the one for the automated weather station. We just multiply by the S, which is already given, 20 microvolts per degree centigrade. And to delta T said here 50, which means it changed 50 degrees, maybe 0 to 50 or 10 to 60 or 20 to 70. So I found the answer. And here where we had some problems in identifying the wind speed, where we said that we have the upstream and the downstream, the time that it went and came back. Okay, so it found out what was the time it went and came back and subtracted it. The answer was 0.001, and in this case I have the distance. Oh, the distance is 343. Really, I didn't see the distance was given, and that's why I said that we need the distance and we have some missing information. Okay, so let me see the problem here. It says C is equal to 343 meters per second. This is very confusing. So that was the speed of sound, and it was not the distance. Maybe from the speed of sound, I can identify the distance, which means that it went 0.003 and it came back 0.002. Still confusing, by the way, to be honest. So I will not consider this in the problem, but because I feel that there's there's an error in this sense. Okay, so that's all. for what we have, we showed you how to calculate. And if you want more problems, I have more problems here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are the solutions for you to calculate by your own. Okay, so I solved many problems. So you have now many problems to solve. Maybe I did not solve the one for the flow measurement. This is a new one. It's different. So please consider that in solving, and see if you have any problems that you want to solve. Remember the problems I solved in class. Please remember the problem I solved in the problems and in class in the examples in the PowerPoint slides, because it will help you a lot to cover all the parts that you need. So you have multiple choice questions, you will have problems, you will have a critical thinking question, and somehow that's a group of all that will make our exam, inshallah. All the best.